In this presentation, we will study about the 2-bit comparator. On the right hand side of your screen, you can see a comparator in which there is 2 input. I have shown the input by this thick arrow because we can have n-bit binary words as the input. A digital comparator is a combinational circuit designed to compare 2 n-bit binary words. That's why this is shown as thick arrows, showing that it is more than a single bit. Fine. And in this particular case, we are going to compare 2-bit words. The next thing is comparators has 3 outputs. You can see here there are 3 outputs and all the outputs are single bit. That's why I have shown it by a thin arrow. The first output is for the case when A is less than B. The second output is for the case when A is equal to B, and the third output is for the case when A is greater than B. So let's move to the truth table for the 2-bit comparator. As it is 2-bit comparator, the word length will be 2-bit. That's why this is your first word having 2 bits B0 B1. This is your second word having 2 bits A0 A1. And as we are having 4 variables, there are total 16 possible combinations, and we have to find out the outputs, the 3 outputs. So let's start. When both A, B are 0 0, which means both are equal. So this is 0, this is 1, and this is 0, because A, B are equal. In the second case, B is greater than A, so 1 0 0. In the third case, B is again greater than A, so 1 0 0. In the third case, B is 3 and A is 0, so again B is greater than A, so 1 0 0. Let's move to the other case. Here you can see that A is 1 and B is 0. So A is what? Greater than B. That's why the first output will be 0. The second output will again be 0. And the third output is high. In this case, both A and B are same. So 0, 1, 0. In the same way, you can fill all the 16 possible combination. I will fill it down, and then we will move to the K-map to minimize the logical expression. Now I have compared all the cases and written the values of the 3 outputs. You can do it by your own. It's very simple. Or you can pause the video and check your answer. The next step, once we are having the outputs, is the K-map. So again, to save our time, I have made the K-map. And there are 3 outputs. So 3 K-maps, 16 cell K-maps. And I have already filled the ones. So the next task is to solve this K-map. So let's solve. Let's change the color. Okay. So for the first case, when A is less than B, this is my first group. We are left with 2 ones. So this is my second group, and this is my third group. So A less than B is equal to A1 complement A0 complement B0, or A1 complement B1, or A0 complement B1 B0. In the second case, for the second output, when A is equal to B, you can see you cannot do the groupings because the ones are in a diagonal position. So you have to write individually the values. So I'm not writing it down, you can do it by yourself, but I will write down the minimized answer that you will find out after the minimization, which is A1 XNOR B1, A0 XNOR B0. So these are the 2 expressions that we have got for the first 2 outputs. Now let's move to the third output. In this is my first group, this is my second group, and this is my third group. So let's write down the expression for A greater than B, and it is equal to A0 and B1 complement and B0, A1 A0 B0 complement or A1 and B1 complement. So in this way we have to design a 2-bit magnitude comparator, and you can implement these logical expressions in your circuit that we are not going to do in this presentation. So this is the end of this lecture. See you in the next one.